All right, hello, welcome back, everyone. Welcome back to Unit 2. I realize it does say Unit 1 on the page here, and that's because a lot of times people do choose to do this as their Unit 1, which is a topic all about the introduction to functions, function notation, parent functions, transformations, that kind of stuff. Today we're going to do an introductory lesson all about solving functions using function notation, what is function notation, and also talking about what is and isn't a function and how we can tell. So let's get into it. First of all, what is a function? Okay, let's talk about that. What is a function versus what is not a function? So a function is any relation that for every input there is only one output. Or in other words, for every x value, there is only one y value. Okay? For every x value, there is only one y value. And I should say there's only one y value maximum. Okay, because if there's zero y values for a certain x value, that's okay. That doesn't disqualify a relation from being a function. But what does is if we have two different outputs or two different y values for a specific x value. So I'm going to give you an example of some things that would be functions versus what would not be a function. So for example, let's say I have this graph that looks like this. And I'll draw a parabola as well on here. Maybe we'll draw a line. And we'll draw maybe a sideways parabola, the inverse parabola. So how can we tell using a graph? Let's start by talking about using a graph. How can we tell whether these graphs represent functions or not? Well, for every x value, there's only one y value, right? So that means that any part of our function, we could draw a vertical line. We could draw a vertical line anywhere we want, and we only touch the graph once, no matter where we draw it. And that is true for this one. There's no part where I can draw a vertical line and that I will touch two different points at once. So this one appears that it is a function. Okay, same with the parabola, right? Is there any way we could possibly put an x value into a quadratic equation and get two different y values? Well, no. Now, I will mention it is possible, of course, to put in one y value and get two different x values out, right? For example, when y is 0, we have these two x values. But this is not a horizontal line test. It's a vertical line test. We only care about whether or not the same input gives us multiple outputs. We don't care if the same output, if the same y value might have multiple inputs that we could put in to get the same one. So this is also a function because, again, there's no part here where I could draw a negative line or a vertical line through and we would hit 2 points. Same with this line. There's no part on this line or any line at all other than a vertical line itself where I could draw a vertical line and hit more than 1 point. So this is also a function. But this sideways parabola, I could draw a vertical line here and hit 2 points, or many other places as well. So therefore, it is not a function because it fails the vertical line test. Another way to test if something's a function or not is, let's say, for example, that we're putting in inputs. The question we need to ask ourselves is there any possible way to get two separate outputs from this? So for example, when it comes to all linear equations like y equals mx plus b, is it possible, right? Is it possible to multiply an x value, right? Multiply our x value by some number, by m, and then add b and get two different answers by doing that? Well, no, right? When we multiply two numbers together, there's only one answer. And then when we add two numbers together, same thing, there's only one answer. And so therefore, all lines are functions. So every line is a function except for the vertical line itself. That's the only exception to that rule. And then what about quadratics? Ax squared plus bx plus c. Well, let's think about it. Is it possible to have an input, have an x value, and get two different y values out? Well, let's think about it. The first part here, we take a number, which is x, and we square that number and then multiply it by a. Well, let's think. Squaring a number, there's only one answer when we square any given number. Now, when we square root a number, sometimes there is two answers. However, when we square a number, there's always only one answer. So therefore, and then when we multiply it by a, we multiply it by something. Again, same thing. There's only one answer when we multiply two numbers together. If I multiply any two numbers together, there's no way to get two different answers by multiplying the same two numbers. Bx is kind of the same as mx, right? It's just multiplying x, so some number with some other number. And again, when we multiply two numbers, same kind of thing. And then when we add those two things together and then also add c, if we add three things together, is there any way to add the same three things together but get two different answers? Well, again, no. No, there's no possible way of doing that. So this is also always a function. Now we could make the same argument for all polynomials. So we could say that if we had a degree 3 polynomial, that all degree 3 polynomials are functions as well, degree 4 polynomials, etc. Because taking something to the power of 3 or to the power of 4 to the power of 5 and adding it to a bunch of other stuff, again, there's only one output. So we could even say that all polynomials are functions. And that seems like a huge claim to make, but if we think about it, it's true, right? All polynomials have to be functions. Well, I mean, other than the vertical line, maybe. Maybe that's not a function, right? But they must be functions because whenever we take something to any power, we always get the same answer, right? Any positive whole number power, we get the same thing. When we multiply numbers together, when we add them up, when we subtract them, when we divide them, any of that stuff, we always just get one answer, right? There's no way to do blank divided by blank and get two different answers as our results, right? And so that's how we know all polynomials are functions. Good. Now, what's an example of something that's not a function? So I'm going to give some examples of what is not a function next. So let's do that. What is not a function? Y equals plus or minus root x. This is not a function. And let's talk about why it's not. So this is not a function because if there's multiple x values that I could put in and square root and get two different outputs. So for example, let's say I square root anything, literally any positive number. So let's take 25 for example. There's two possible y values if I square root it. There's plus 5 and negative 5. So this is not a function. However, what is a function is y equals plus square root x. This is a function, right? If we're only accounting for the positive side of that, then it's okay. However, if we're doing plus and minus us with a square root, that is no longer a function because there's two outputs for every positive input, and that's unacceptable. Now, in terms of, you might ask, well, is it okay that not all inputs are possible? Yes, that is okay. It is not the requirement for a function to have every single input possible, but it is a requirement that for every input that is possible, there's only one output. So it's okay that negative numbers can't be, that x can't be negative numbers in either of these cases. That's not what stops this from being a function. What stops it from being a function in the first place is that we could possibly put an x value in and get two separate y values, and that shows that this is not a function. Very good. So most of the things we'll talk about in the course are functions, as this is grade 11 functions, but we will also dabble in what is not a function as well. There can also just be some various examples in real life where we talk about is it a function or not. So for example, let's say our x variable is the eye color, and our y is the batting average. Let's use that as an example. So my question here would be, is it possible that two people both have the same eye color but have different batting averages? Well, yes, of course that's possible, right? I'm sure there's lots of people, especially most people in the world have brown eyes. I'm sure there's plenty of brown eyed people who have different batting averages, but the same eye color. So we could input the same eye color of brown eyes or blue eyes or any other color of eyes and get two different or even more different possible batting averages. So this is not a function because it's certainly possible to have the same input, say, oh, I want to know what do the blue-eyed people bat, and get multiple different answers for all the different blue-eyed people. Or same with brown-eyed people or any color of eyed people, right? Or hair color versus batting average, same kind of deal. There, it's very possible, right? Or let's say we have math mark and hair length. Well, again, this is also not a function because two people could have the same math mark. I could input the math mark 93% into my computer and output two different hair lengths, right? There's not just, oh, only people with this hair length have this math mark. Well, no, two people could have the same math mark, so same input, but have two different lengths of hair. Now let's give a real world example that would be a function, right? Let's say that we have, oh, I know. Okay. Let's say we have like time versus the height, for example, right? Um, Time is our input, and height is our output for I throw a ball, right? Let's say the scenario is I throw a ball and there's a time and a height. Well, is it true? Is it possible for the ball to be at two different heights or multiple different heights at the same time? Well, no, this is not possible, right? If I choose a time, there's only one height the ball is at that very time. There's not going to be, oh, the ball at 3 seconds, it's at 5 and also at 3 meters or, whatever unit we want to use. Well, no, that's not possible. So therefore, time versus height, this would be a function. So this would work. Okay, so that's the basic of functions. Now let's talk about using function notation. So basically, instead of saying y equals all these things, we can use something as a function of of x, right? So for example, f of x equals 3x plus 5 rather than y equals 3x plus 5. So f of x is replacing y. Or we could do it with a quadratic. F of x equals x squared, right? We discussed how all quadratics are functions, or at least all quadratics with the ax squared plus bx plus c model must be functions. Therefore, y equals x squared is a function. We can switch it to function notation. We don't have to use f of x, though. We could use g of x or h of x or p of x or any other number of things. And oftentimes you'll see f of x used in most questions. However, whenever we're trying to show that there's two separate functions, we must use a separate notation. So for example, in the same question, you're not going to see f of x equals 3x plus 5 and f of x equals x squared. You might see f of x equals something, g of x equals something, h of x equals something, just to show that these are three different equations in our same question. That the function's not changing, it's just that there's three separate functions. Now let's say I want to evaluate the function of what is f of x, or what is our output when x is 2. I could put in f of 2 equals 3 times 2 plus 5 equals 6 plus 5, which is 11, right? So therefore, our y value, or our f of 2 value, is 11. And let's say we do g of x is x cubed, for example. Well, g of 2 would be 2 cubed, which is 8, right? So basically, it's the same as solving any equation, right? Except we're looking at the equation instead of y equals the answer, right? We're looking at it as a function of x, right? That if we input a certain value for x, it will spit out a certain value, and it will be the same thing regardless, right? There's not going to be a way to have two things. If there are, then it wasn't really a function in the first place. So let's do some examples regarding solving equations using function notation. Here it says h of x equals 4x plus 1. Find x when h of x equals 9. Okay, so let's be clear here. This is not where x equals 9 and we have to find h of x. This is where h of x equals 9. So I'm going to replace h of x with 9 and find out what x is. So here I replace the h of x with 9. Now I'm going to solve. I'm going to say therefore 8 equals 4x. So therefore x is 2. So therefore we found x. We found out that x is equal to 2 when h of x is equal to 9. So we found out that when the output is 9, the input is 2. Now don't be fooled. It is possible for there to be multiple multiple inputs for the same output. That's okay. However, in this situation, it's a line, and so there's only going to be one, right? Okay, let's try this one. Negative 3 equals 4x plus 1. So therefore, negative 4 equals 4x, and therefore x is equal to negative 1. And there's our answer. Voila. So same as solving other equations we've solved, probably for 5+ years at this point, maybe more than that, maybe less than that, but somewhere around that ballpark, except that we're using a different notation now, where we replace y with h of x or f of x or g of x or some sort of function notation. All right, here's another one. It says, what values of x make f of x equal to 0? So this one is similar to our quadratics from earlier that we did last unit. 0 equals x squared plus x minus 12. Or it says 1x, but I wrote x. It's the same meaning. Okay? So I need to figure it out. I need to solve this. However, it's the same thing, right? I just replaced f of x with 0. So 0 is equal to x minus 4, x plus 4, x minus 3. So therefore, x is negative 4, or x is equal to 3. Now, if to you this going from here to here or from here to here was a leap, I do suggest reviewing the factoring quadratics unit because it talks all about that there. But the point here in this lesson, for the sake of today's lesson, is that f of x is equal to 0 and we're replacing it. I will talk briefly about how I got here though. So for this one here, what I did is I said, what are two numbers that multiply to negative 12 and add up to 1? I figured out that they were 4 times negative 3 would get us there, or 4 plus negative 3 would get us to 1. And I used them here. And then I used our zero product property to determine that x is equal to negative 4 or 3, right? If I plug in x is negative 4 back to the equation, I'll get, in these brackets, I'll get negative 4 plus 4, which is 0. And 0 times whatever the next thing is, 0 times whatever this is 0. And likewise here, right? If I plug in x equals 3 to the second one, I'll get 0 times, whatever the other one is, which I think is 7, but we don't really care what it is. We get 0 times something, and that also gives us 0. Now, I do go into more detail on that in previous lessons, so do go review those, go check those out if this was confusing. But that's the basic knowledge on that. All right, here it says, what values of x make f of x equal to 44? So 44 is equal to x squared plus x minus 12. Okay, so let's do it. Therefore, 0 equals x squared plus x minus, would be 56? Yeah, minus 56. Okay, so now I need two numbers that multiply out to 56, or negative 56 rather, and add up to 1. So let's see, maybe 8 and 7, or some combination of that. Yeah, 8 and negative 7 would work. And so these are our answers. So here, it's the same as other things we've learned. The difference is we used function notation to sub in, instead of a y equals value, an f of x equals value. But that's the only difference between this and what we've done previously, is just the notation. Everything else is review, essentially. Okay. I think I have three more, or I guess two more examples. I guess really four more examples because example 4 does have three parts to it. So about four more examples here that I want to discuss. Here it says, given g of x equals x squared minus 3x minus 12, what values of g of x equals 6? So I'm guessing what x values of g of x are equal to 6. So let's do that. Let's say 6 is equal to x squared minus 3x minus 12. Therefore, 0 is equal to x squared minus 3x minus 18. And what are two numbers that multiply to negative 18 and add up to negative 3? Well, 6 and 3, or some combination of, right? Negative 6 times 3, or negative 6 plus 3 will work. Sorry, that should look more like a plus, not a times. There we go. That's a better plus sign. X minus 6, x plus 3. So therefore, x equals 6 and x equals negative 3 are our answers here. Very good. All right, and for our last example, here they're asking if f of x equals 4x plus 2 and g of x equals negative 2x plus 14, find x in all the situations. So let's start with the first one. The first one says if f of x is equal to g of x, if they're the same, what's the x value here? So if 4x plus 2, which is same as f of x, is equal to g of x, which is negative 2x plus 14, then what's x? That means 6x is equal to 12, therefore x is equal to 2, so x is 2 is our answer here. Now what about this one? F of x plus 1 equals g of x minus 8. Well, what is f of x plus 1 first of all? Well, f of x plus 1 is equal to 4 times x plus 1 plus 2. Notice all I did here is every time I saw an x on here, I've replaced it with x plus 1, right? Because instead of the function being of x, it's of x plus 1. And so every time I see x, I replace with x plus 1. And then I'm going to solve further for what this is equal to, right? So this is equal to 4x plus 4 plus 2, which is 4x plus 6. So this is equal to 4x plus 6. Now what about g of x minus 8? Well, I'm going to use the same technique, except this time, whenever I see an x in this equation, I'm going to put x minus 8 instead of just x, right? Because here we're replacing x with whatever's in those brackets that used to have an x. So we're replacing it with x minus 8. So negative 2 times x minus 8 plus 14. So that's negative 2 plus, or sorry, negative 2x plus 16 plus 14. That's negative 2x plus 30. So this is negative 2x plus 30. Now let's equate the two and find the answer. So the answer is 4x plus 6 is equal to negative 2x plus 30. So therefore 6x is equal to 24. Therefore x is equal to 4, and that's our solution. Okay. Now I encourage you, I guess there's two B's. This should really say C. My apologies for that. So now that I've relabeled this, I recommend everyone tries C by themselves. Give it a go if you feel comfortable doing that, and then come on back, and I will take up C as well and talk a little bit about some homework and some practice you can do. Okay, so let's do it. So f of x minus 1, well, what's that equal to? That's equal to 4 times x minus 1 plus 2. And then 2x plus 1, so negative 2, 2x plus 1 plus 14, right? So notice how in our original equations, whenever there was an x for the f of x, I replaced with x plus 1, and for the second one, I replaced with 2x plus 1. And now all I need to do, that I've put it in this form, is just solve. So 4x minus 4 plus 2 equals minus 4x minus 2 plus 14. So that's 4x minus 2 equals negative 4x plus 12. So that's 8x equals 14. So that is x equals 7 over 4, and that's our final answer. If you have any questions, feel free to write those in the comments below. I will be checking those comments for any questions, and also you can help your peers out as well if you'd like to and answer some of their questions. And I do have some suggested practice problems for this, and they include the questions from the handout for function notation that are here. So I do recommend completing that handout. There's also this handout about solving the equations using the function notation. So do give those a try. Those are some of the suggested problems. And that's everything for today. Next day, we'll talk about parent functions and their transformations. So have a great rest of your day, everyone, and we will see you next time. Bye.